Yeah, just a few things let's talk about. Yeah, get a calculator. Okay, so next week in lab, we're actually going to be making some solutions. So this is the official solution preparation routine. You measure out, you figure out how many grams of something you need. We've actually done this calculation. Use the molarity calculation, turn the moles into grams, and then you measure out that number of grams, put it into a solution, add some water, and swirl it. We're going to leave the flask out of the scenario. We're just going to put it right into the thing we're going to use, which is going to be an evaporating dish. But this is how you do it. But what I really want to talk about today is the dilution and concentration formula, which is this. Okay? We talked about this at the beginning of our discussion about solutions, and it simply states that if you want to dilute or concentrate a solution, you take the molarity and the volume of the first thing and set it to equal to molarity and the volume of the second thing. Okay? It's just M1V1, molarity and volume of the first solution, equals M2V2, molarity and the volume of the second solution. So if you make something more dilute by adding more volume, your volume goes up, your concentration goes down. If you allow something to evaporate, the volume will go down and the concentration will come up. Does that make sense? Okay, so we're going to do a couple of practice exercises. I have a solution over here. What is the volume of my first solution? Just tell me. You throw something out. 5 milliliters, or 5 liters, okay. And what's the concentration of my first solution? 20 molar, okay, 20 molar. Okay. Now we're going to change it. We're going to make it more dilute by increasing the volume. What's the new volume? Let's make it. Let's do something we can't just do in our head. 7, okay, so 7 liters, and now we need to find M2. So can you do that? Yeah. So bang on the calculator for a little bit, let's find M2. Using our formula, M1V1 equals M2V2. Okay, so did you get a number larger than 1? Yeah. Larger than 5? Yeah. Larger than 10? Yeah. Larger than 15? No. What'd you get? 14.28. So 14.28. 14 molar. Okay, which should make sense because we increase the volume, so we decrease the concentration. Make sense? Yeah. Okay. Now let's look at our second second concentration. What's the new volume of our first solution? 6. 22 liters. Okay. And the concentration? 27 molar. All right. Now we're going to allow it to evaporate for a while. We're going to expose it to the environment, let the water evaporate. What's the new volume? Oh, wait. This is something we can't do in our head. 12. Okay. 12 liters. And what is our M2? So I'll let you solve that. So in this case, we're going to allow the volume to drop. So we would expect our concentration to go up. Good. So let's find our M2. Simplest thing in the world, simple single variable algebra, just solve for the thing you don't have. Lord. Magic Lord. Okay, so hopefully we get a number that's larger than 27 because our volume is going down, so our concentration should go up. If you got a number larger than 27, raise your hand. Yay, larger than 30? Larger than 40? Larger than 50? What'd you get? 49.5, so about 50? About 50 molar? See how that works? By the way, I can't think of a single thing that's 50 molar. That's like super concentrated. Most of the things we're doing are like 0.1, 0.2, 1, 2. But you know, 50 molar would be like soup. Yeah, it would be like gel. It'd be super concentrated. Okay, so does this idea make sense? Any questions about this? So you feel pretty confident to be able to dilute or concentrate something?
Yes, sir.
Cool. Last thing we need to talk about, colligative properties. I was surprised so many people didn't understand why you put antifreeze, or what we call in the desert anti-boil, in your radiators. Why do you put ethylene glycol or propylene glycol, that orange or green goop, why do you put that in your radiator? Yeah. You use water in your radiator, unless you have an electric car, you have a radiator in front of your car, and what happens is water gets pumped through the radiator, then through your engine block, through little channels, there's little tubes, little metal channels that go through your engine block, and then that hot water goes back to your radiator where it cools down, and it goes back to your engine. That keeps your engine from blowing up. Yeah. Keeps your engine from burning up, because realize those little explosions happen thousands of times a minute in your engine. They get really, really hot, so you got to cool your engine down. But I was surprised when people don't understand why you just don't add pure water. Pure water is actually a better coolant. Why don't you just add pure water?
Because they'll freeze.
Exactly. In Minnesota, pure water will freeze in your radiator. And in the desert, pure water will boil in your radiator. So what we do is we add an impurity. We add ethylene glycol or propylene glycol. And the way the impurity works is like this. If the bell rang and you all wanted to get out of the room, you're like, freedom! And we put a big fat guy right here in the door. It's going to take you a lot longer to get out of the room.
You'd be surprised.
No, not like a big fat guy, like a big, like bouncer kind of, you know. But it's going to take you a lot longer to get out of the room. And that's how the impurities work. You put a big fat guy within the water molecules. In fact, billions upon billions of big fat guys with the water molecules. It keeps the water molecules from freezing together, and it keeps them from boiling at the surface. So, and it's the more fat guys you have, the more impurities you have, the harder it is for the water to boil or freeze. And that's the heart of colligative properties. Colligative means depends upon amount. In other words, the more junk you have, the more you will change the properties. The more impurities, the more ethylene glycol that you have in your radiator, the more impurities you have, the more it's going to change the boiling point and the freezing point of water. And those are usually the physical properties we talk about. Pretty much all physical properties are going to be affected by colligative properties, but the ones we care about are the freezing point, the boiling point, and the vapor pressure. We use the stuff in a radiator so our radiators don't freeze in Minnesota and don't boil in Nevada. Delta T equals Km. The change in temperature equals K times what's called molality, special kind of concentration. In this class, you won't actually have to calculate colligative properties. You'll just have to know how they work. In other words, you have to know that the more junk you have, the lower the freezing point, the higher the boiling point. But we'll save the calculation itself for AP chemistry. Thing to talk about. Something you've actually seen before in biology. And the thing we're going to be talking about is osmosis. When you hear osmosis, what do you think about? Someone always says that. I've never seen that movie, but maybe I should. Osmosis, germs! No, think about academically. When you hear osmosis, what does that usually mean? Interesting. Okay. Well, when I was in high school, something you could do, and you can't do now apparently because everybody gets freaked out about blood, is you could take a drop of pig's blood under a microscope, and then you would add salt water to it. Salt water to it. And if you add salt water to the pig's blood, the little red blood cells under the microscope would shrivel up. And if you take pure water and add pure water to the pig's blood, the red blood cells would swell up and pop. They swell up like little inner tubes and they'd pop. Yeah, it does sound cool, but nobody does it anymore down here because they're all freaked. Oh, blood!
I'll give you blood.
Well, I don't want your blood, but maybe if you get a big juicy steak that still has a little bit of blood in it, then you could do that with your microscope. You could add pure water and salt water to it. Osmosis is the Bernie Sanders of science. Osmosis wants everything to be the same. So if on one side of a barrier you have very, very pure solutions, and the other side of the barrier you have very, very concentrated solutions, the solution will try to move across the barrier to make both things middle ground. Okay? So the solution is the travel of a solvent from an area of low concentration to an area of high concentration, or an area of high purity to an area of low purity. We want to make everything the same. So if you got a rich solution over here and a poor solution over here, osmosis tries to make both sides about the same. I'm sorry? And here's my little diagram of the pig blood, red blood cell. You put a red blood cell in a solution that's very, very concentrated, and the water will try to come out of the red blood cell to make that solution less concentrated, and it will shrivel up. On the other hand, if you put a red blood cell into pure water, the pure water will try to go into the red blood cell to make it less concentrated, because it's less concentrated. Socialism. Socialism at the scientific level. If you ever wonder where pickles come from, there's no pickle tree. Nobody digs pickles out of the ground. They come from cucumbers. When you put cucumbers into a concentrated brine solution, concentrated salt solution, then the water gets osmosed out of the cucumber, and the cucumber shrivels up. I'm a cucumber, not a pickle. Carrots do the same thing. If you want to store your carrots and your celery for a long time, you can put them in water, and the water will go into the carrots and the celery to keep them firm. Unfortunately, over time, that process will actually make the celery turn white. But works well with cucumbers and celery. And, with most vegetables, you keep them in water, they'll stay firm. Uh-huh. It just doesn't taste as good if it's white. Yeah. Okay. Any questions about this osmosis stuff? Yeah. Yes.